Welcome to Ballari Institute of Technology and Management.
Good evening, sir.
Hello. Yeah, am I audible?
You are audible, sir.
Okay,
Audible,
thank
sir?
you. Yeah. So good.
Just a minute, sir. I will make you speaker, sir.
Because, sir, it is audible. Hello.
Yeah, we can hear you. Yes. I think so.
Audible, sir.
Yeah.
Sir, little we can wait for 2 minutes, sir. Let other participant can join.
Fine. So I'll be online. So let me know. Okay. Yeah.
2 minutes, sir.
Okay. So we'll anyway. So it starts at 5, right? We still have 10 minutes. Okay.
Yes.
Yeah.
Sir, still 10 minutes is there, sir. We can wait for 5 minutes. We can start.
Okay.
Everything a student needs. Situated in Karnataka's Steel City, Ballari. BITM is ISO certified and conforms to international standards by creating and implementing a quality management system. BITM offers undergraduate and postgraduate programs.
I'm currently pursuing
Shete camera on cheyi.
Raghavendra Shetty, sir. I think sir has joined. You can start, sir.
Sir, shall we start the session, sir?
Yeah, we can start. Go ahead. Yes, yeah.
Yes, sir. Thank you.
Yeah, if you want to wait for participants, we can wait. Not a problem. So I see only 8. No, your voice is very feeble, Mr. Sethi.
Sir, now it is audible, sir.
Yeah, it's better. Yes, yeah.
Okay, sir. Okay, sir. Thank you. Sir, now, sir, sound quality is okay, sir?
Yeah, it's okay. It's manageable. Yeah.
Okay, sir. Thank you, sir. Good evening to one and all. I, G. Raghavendra Shetty, co-coordinator of this FDP and working as assistant professor in the Department of Mechanical Engineering, Ballari Institute of Technology and Management, Ballari, Karnataka. I take privilege in introducing today's resource person, Dr. Murugayan Amurthalingam, sir. Sir is the assistant professor in the Department of Metallurgical and Materials Engineering, IIT Madras. He is in the teaching profession since 2016. He has received his Bachelor of Engineering in Metallurgy Engineering from Government College of Engineering, Salem in the year 1999. Then he pursued a Master of Science by Research from IIT Madras in the year 2003 and PhD in Joining and Additive Manufacturing from Delft University of Technology, the Netherlands in the year 2010. He has taught various subjects at undergraduate level and postgraduate level. Being a supervisor, he has guided 3 postdoctoral fellows, guiding 12 PhDs, 5 MS by research, 8 MTech projects. Sir has participated in more than 50 conferences in national and international level, authored 3 book chapters and 38 plus referred international journals with 1 Indian patent. Our beloved resource person, awarded and honored by Placid Roderick Memorial Lecture Award from Indian Institute of Welding in the year 2020. Kenneth Eastering Award from International Institute of Welding in the year 2015. Welding Torch of Honor from Delft University of Technology, the Netherlands in the year 2015. It is pleasure to have you with us today, sir. Thank you. Now I request Dr. Murugayan Amurthalingam, sir, to take over the session.
Yeah, thank you, Sadi. I mean, it's not required to introduce elaborately. Okay, so thanks. Okay, so apologies for not presenting yesterday or day before yesterday because there was some personal issues. So we'll start the slides. Yeah, is my screen visible?
Yes, sir. It is visible, sir.
Okay, fine. Thank you. So the idea of this presentation, what I'm going to talk about next 1 hour or so, is to give some fundamentals of IT manufacturing. You must be hearing about IT manufacturing in various forums and even this FDP also. A lot of people must be talking about the techniques. So in this talk, I just made it more of a fundamentals and to describe about the various techniques that are available for additive manufacturing. and they are academic terminologies and the generic process chain, what we follow for additive manufacturing process. So therefore, I'm not going to talk about the case studies or the research what is currently being carried out in IIT Madras or elsewhere. If you need more information about the state-of-the-art research, what we are doing, you can also look at our papers and publications. Okay, so just to give brief introduction about the additive manufacturing. So additive manufacturing, you must be hearing, it is not as in a conventional manufacturing, but we use a subtractive or formative techniques where we use an defined tool to fabricate the components of the shapes and the properties required. Say for example, for producing and cylindrical or the spherical ball of a defined shape in a conventional manufacturing process. So we'll have to start with a cube which is made by either casting or forging process. Subsequently, we will have to carry out extensive machining to produce such a process in the combination of both formative and subtractive manufacturing. So in additive manufacturing, we produce the same shape.
Excuse me, sir.
Yes.
Slides are not visible, sir.
It's not visible?
Yes, sir. Yes, sir. Can you reshare, sir?
Is it not visible?
Just a second, sir. I'll make you. Yes, now we can share your slide.
Is it not? Now it's visible?
Just a second. No, it's not visible, sir. Sir, you can share the screen, sir. Yes, sir. Yes, sir. Visible.
Visible?
Visible. Sir. Yes, sir.
Yeah.
Yes.
Okay. So we were looking at the main difference between the subtractive and additive manufacturing, right? So in the additive manufacturing, so for example, to realize that sphere, so we can first create the basic design, and then we can also manipulate the three-dimensional data into two-dimensional data format, which I will talk about in subsequent slides. And then we can build the same shape layer upon layer. Okay, and we can use multiple techniques to produce that shape based on the feedstock material we want to use, and then the surface accuracy, the surface roughness accuracy, as well as the dimensional tolerances what we have, and we can choose one of the techniques to manufacture such a part. So as a definition of additive manufacturing, so it is refers to the process of joining materials to make parts directly from its 3D model data. So we don't use any part specific tooling like we use it for a casting or forging, where we need a tool to shape the component. Okay, so here we directly start from the CAD data, and then without any part specific tooling, so we realize the end part layer by layer. Okay, so the important attributes of additive manufacturing is a fully automated operation. So from the CAD data and the final production, we do it in a fully automated way, converting the digital design into a physical object without any part specific tooling. So these are the main attributes of additive manufacturing. Okay, so you may see this additive manufacturing is named various names like rapid prototyping, rapid manufacturing, 3D printing, solid film fabrication, direct digital manufacturing, and etc. So all of them now we don't use them. Even 3D printing, it's a more colloquial term. So the academic term is an additive manufacturing what we use. So when we actually use metals and alloy feedstocks, okay, there is a direct connection between welding and joining, because here the process of creating an object layer by layer, it is an analogous to the welding process, a multi-pass welding process what we do. So in the multi-pass welding, what we do is the pass by pass we deposit the molten material, and then individual layer, individual pass is joined with the previous pass. So therefore, the physics of the process is directly coming from the welding when we use a technique for full melting. The video I show over here is the printing equipment what we have in IIT Madras, where we use one such technique in which the feedstock is actually contained in a powder bed, and then the laser selectively melts at a location where we want to create a melt pool. And then the molten pool solidifies. The next layer of feedstock is spread on top of the previously deposited layer, and then laser again melts the new powder layer what is spread on top, and then this molten powder, okay, the layer weld with the previous layer. So this is one technique of IT manufacturing. This is most commonly used to produce the metals and alloy components, which requires very fine features. Okay, the other techniques which we use it for producing large components. Okay, or if you want to use polymeric materials or ceramic materials, and we can think about other processes which I want to tell in this lecture. Okay, so timeline, if you look at when does it all happen? If you look at additive manufacturing as such, it is not so new. Okay, so the first patent, in fact, of realizing the component in a welding based process, so where one person he used a welding torch and gas metal arcing torch, and then he started depositing layer by layer to produce a final part. That patent was actually filed in 1924. Okay, even before our independence. Okay, so before Second World War. And as a welding, scientists and welding professionals, people call that as a multi-pass weld, okay, or what you call as weld overlay. And weld overlay was actually used to fabricate, near net shape components for a long time. But then, actual the technique of producing final component, okay, layer by layer, and in a new era was patented by a Japanese scientist named Hideo Kodama. Okay, Hideo Kodama first he realized the fabrication of a component using photopolymers. Okay, so these photopolymers are nothing but like our paint we apply for the wall painting, right? So when it is exposed to sunlight, the liquid paint cures and becomes solid. So what the scientists did was actually he took the photopolymer in a container, a vat, and then he selectively exposed only few locations for light photons. So moment light photons falls onto the location when the polymer cured. And then he added a next layer of photopolymer on top of it, and then he cured again, and then he created the object, the final first part, okay, using the technique what he was actually called as vat photopolymerization. And then similar time, Charles Hull, a very famous scientist in US, he also developed using lasers the same technique of curing photopolymer selectively at a location where we wanted to create a solid. Okay, so and then he called that as an SLS, stereolithography apparatus, or SLA process. So he patents, and then he started selling the equipment in the name of 3D systems. So that's where all started. And then people started using that equipment for prototyping, rapid prototyping using vat photopolymerization, and started. And the same company, 1992, they also came up with one of the startups of 3D systems, a branch out company, and DTM startup. So they came up with equipment where lasers can be used to selectively sinter the metal powders. So the selective sintering of the metal powders when it spreads and then layer by layer sintering can create a green powder compact, and that can be sintered to produce a brown part. Okay, so that was actually first commercial metal additive manufacturing equipment came up in the market in 1992 from the DTM startup from 3D system. They call it a SLS machine, so selectively laser sintering equipment. So once people realized, a lot of research went on to develop the equipment for 3D printing or additive manufacturing for metals and any equipment. And then in 95 onwards, there was an explosion of scientific research to produce 3D components directly from design in various techniques. And we are now in the situation where the academic research is actually now taken to next level, where the components are also commercially produced by using this technique, even in the regular production. Okay, so from 1990 to 2010, if you see that, a lot of equipment, a lot of manufacturers, they came up with their own technique. Right now, we also, almost all the metal additive manufacturing equipments, they involve a full melting. That means that we can create a molten pool, and the molten pool solidify, and then we can create the object layer by layer by welding of layers. So this is a broad timeline for additive manufacturing. So if you look at the history between in 90s and right now what we have. And simultaneously, the other techniques like laser wire or welding based setups, they also came up to produce a large volume components as well, which I will discuss in subsequent slides. Okay, so what is the state of the art now in additive manufacturing? If you look at, so this slide shows the current research and the development what we see here. So, and there are efforts to print the bio organs using additive manufacturing. So these are a mice part, kidneys and the bones using an hydroxyapatite based ceramics. Okay, so these are all 3D printed objects, and I've seen recently one of our collaborators in Netherlands. So they were also printing and sensors on a lung, working lungs of a patient. So they additively manufactured a sensor on top of a human lung, which is working. So a lot of developments are actually taking place in terms of biological applications, and this is a prosthesis limb. Okay, so which is additively manufactured using material extrusion based techniques. And the advantage of additive manufacturing for prosthesis development is we can precisely produce the prosthesis objects as per the patient's organ. So because of that, rehabilitation time reduces significantly and the comfort also increases. And we also actively collaborate with our defense services to produce these processes as per the patient's organ. So we also work extensively on producing bioimplants. So one such implant is shown over here, and this is what is known as a cranial implant. So these implants are very crucial and life-saving implants. These implants are used during head injury. Okay, so when a person undergoes a head trauma, the surgeon instantly releases the pressure which is accumulating in the skull by cutting open the skull bone. Okay, so subsequently the opened part of the skull should be closed by the implant. So these implants are generally made of the titanium or a polymer, biocompatible polymer implants. And making this such an implant, such implant generally by conventional manufacturing method is highly time consuming. Okay, so imagine a surgeon performs this the cranioplastic surgery. The moment the skull is opened, the patient is induced to coma until the implant is made and then placed onto the person's skull. Right. So each of our body is unique and different, isn't it? So therefore these implants, it is made once the CAD, the CT is done, and then CAD drawing is generated, and then an implant manufacturer can produce that implant based on the CT data what we receive. So it takes about about a week or so sometimes to make these implants made and then shipped to place it on a surgical procedure. So in additive manufacturing, we are now printing such an implant instantly, because the moment the CAD data is generated from CT scan, okay, so we can instantly create the CAD drawing, and then subsequently CAD drawing can be used to print the implant, and then we can get the implant made in 3 to 4 hours. So we have actively collaborating with a startup in Chennai to produce such implants, including the maxillofacial reconstructive implants. So those implants go in the front part of the face. Okay, so to replace the maxilla. Maxilla means the front jaw bones. Okay, and dental bones, especially for children, it is very crucial. So then when they undergo an accident, the jaw bones will be reconstructed, or the frontal maxilla bones will be reconstructed again. So that requires a quick time to realize those implants. And the material what we use is also very difficult to machine. For example, titanium or cobalt chrome alloy. Okay, so therefore, and using additive manufacturing to print those parts are highly recommended. And we also save a lot of life. So we printed close to 120 implants already, and it's placed on the patients. Okay, so this is biomedical application what you see, and some application for engineering. Okay, so this is a turbine blade made by Siemens, and you see this there are complicated cooling channels inside these turbine blades, and these channels are effectively reduce the operation temperatures of these turbine blades, so therefore increasing life of these turbine blades. And introducing such a cooling channel inside the blades in a conventional process very difficult. So because we print layer by layer, introducing cooling channels are very nice. And similarly, the cooling pads what is printed by GE. So these are for turbine applications. And this is a 3D printed house. You must have also heard in the news that IIT Madras, first time in the country, we completely 3D printed from the scratch a 3-bedroom house in our campus directly from data, CAD data. So we 3D printed entire 3-bedroom house using this process. Right, so and these are all state of the art. But you see now we are actually taking this technique of 3D printing house to print shelters in the borders. Okay, to help our soldiers, or using this technique for building houses where it is required in terms of natural calamity, or to providing an affordable houses in the remote locations. If you look at the IT manufacturing nomenclature, you can broadly classify into single step process or a multi-step process. What is single step process? In single step process, we produce the end use component, okay, directly from the printer. And this is one case study carried out by a very famous company where they wanted to produce this seat assembly of an aircraft. Say when you fly an aircraft, you sit, and then the seat of a passenger is connected with the fuselage body by using these assembly. And if you look at this part is actually designed to make this part by conventional manufacturing method. Okay, and you see a lot of material, and then based on the ability to produce by conventional forging and welding, so we produce this part. But we don't need such a heavy part. We can also reduce the weight of the part by optimization. Okay, so we can redesign the entire part by looking at the stress analysis, how the loading is actually happening in real life, and then we can reduce the significant amount of material. But then the part geometry becomes extremely complex. Okay, so to realize such a complex design containing part, okay, we cannot use a conventional manufacturing. So for making such part, you can't do a casting process. It will become very brittle, and then it is also difficult to produce thin sections. So therefore, the only best way is to just print it. So we design redesign the part, okay, because of the design freedom what we have in IT manufacturing. So we can develop, right, and a complex design, and subsequently we convert a CAD drawing and do a slicing and path planning and print it and realize the final part. And this part can straight away be used in the end use. So this is a single step process. And some processes we require multiple steps in additive manufacturing. For example, if you want to produce a ceramic component, okay, ceramics, when we actually want to print, okay, so you can melt a ceramic particle. For example, if you want to produce an aluminum oxide component, or silicon carbide, or tungsten carbide, for example. So what we do is, again, we start with CAD data. And then we use technique like, for example, binder jetting, where we mix the powder, okay, with binder selectively at the location where we want to create a solid object, and then subsequently powder which is mixed with binder is heated up to debind and then subsequently sinter the part so that we create a dense component. So this requires multiple steps. For example, first printing and then post-processing to debind and then sinter the part. So therefore, this is actually a multiple step processes. So in additive manufacturing, so whether you can do in a single step component fabrication or multi-step process and a component process as well, based on the feedstock what we use or the properties what you want to achieve at the end component. Okay, so what are the benefits of additive manufacturing? Okay, so again, so I'm just showing in a case studies what we have carried out to produce a component of titanium, okay, in standard manufacturing methodology and by additive manufacturing, and then see how much material energy we may save by moving to additive manufacturing. For example, so this is the component, aircraft component again, made of titanium, okay, Te64, titanium, 6 aluminum, 4 vanadium. It's a famous titanium alloy, alpha plus beta alloy, we have to call it. So to produce such a component, first we need to start from a huge billet, 20 kg of billet of titanium, and titanium production is extremely energy consuming process. So we'll end up producing, okay, large amount of carbon dioxide, okay, which is a greenhouse gas, isn't it, during the production of such a massive amount of titanium. Okay, 20 kg, 900 kg of CO2 is released, and then we end up generating spending about 10,000 megajoules of energy, and then subsequently we'll have to do machine the part and then weld it to produce a component. And during this process, so we spend about 10,000 megajoules and then release about 900 kg of carbon dioxide, and remaining materials wasted as a scrap, and then that should be recycled again. That will also consume more amount of material and energy. So as compared to standard manufacturing process, suppose if you want to print by additive manufacturing, so say for example powder bed process. So we start with about 1.1 kilogram of billet, we atomize, do printing, and then get the part. Okay, so the amount of energy you spend is not even about 600 megajoules, and then you save about 95% of material. And then we also save a large amount of greenhouse gas emission during this process. So therefore, the material and energy saving is one of the biggest advantages, okay, by moving from a conventional manufacturing to additive manufacturing. So what are the other benefits? Okay, the other benefits are design freedom, what we have. Because we produce layer by layer, okay, so we can also visualize, okay, very complex shapes containing components. For example, here I show, okay, and lattice structures, and these structures, they possess unique properties, auxetic property. So what is an auxetic property? So an auxetic property, so when we apply a tensile stress in one direction, okay, in a conventional material should shrink in other direction, in orthogonal direction, isn't it? That is coming from the Poisson effect. Whereas these materials, when you apply tension in one direction, they also expand in other direction. So these materials possess negative Poisson ratio. Okay, and these negative Poisson ratio materials, they design the components, have excellent energy absorption capabilities. Okay, and our bone is a negative Poisson ratio material. Okay, and these materials we call it an auxetic material. So our bone replacement implants, so when we actually design, and we should design the implant which can possess the auxetic property. And imagine to introduce this auxetic property, we'll have to design very complex cell structures. And these structures, if you look at, for example, here honeycomb structures. Honeycomb is an auxetic material, the component. And producing such a complex shaped component by conventional manufacturing, it is impossible. Okay, so because of the advantage where we have a layer by layer manufacturing, we can fabricate such a complex shaped structures, and the material with internal cooling channels. Okay, here, so you see some cooling channels containing a component where cooling fluid can be transported inside so that the surface is cooled very effectively. Okay, so for applications like, where we work material at high temperature, the tool should withstand, okay, the temperatures. The most of the time tool fails by the thermal fatigue, makes repeated heating and cooling. So if the tool is cooled, okay, and then the temperature of the tool is maintained, so we expect the tool life to increase significantly, and the performance of the component as well when the component is exposed to high temperatures. And you see some of other complex designs, what we actually can use it for various engineering applications, including the conformal cooling channels. Okay, so what we have, okay, all these things are possible only by additive manufacturing. Okay, so in a conventional manufacturing, what you see is what you get, right? So whereas here what you see, that is what you print. So therefore, okay, so you can visualize and make a CAD drawing, and then you can realize that part. Okay, so with extremely in a cost and time effective manner, and the process is fully automated. Okay, because the entire process chain can be controlled, okay, unattended operations without any part specific tooling. And if anyone wants to change the design last minute in a conventional manufacturing, it is not possible. Right, so we'll have to go back and change the entire process chain, including the equipment, tools, and everything to change the even a small chain design. Whereas in here, you can see that some design change should be accommodated. We can quickly do that as well. Okay, and we can introduce effective design as I talked about, and then we can also introduce new materials. For example, okay, so the material selection for any engineering application or biomedical application is strongly dependent on the manufacturing methods. Right? For example, for a casting of aluminum alloys, we always prefer to use aluminum silicon alloy. So why? It is castable. If you use any other aluminum alloy, it may crack, okay, during casting process. So therefore, the selection of material is strongly dependent on the manufacturing method. But some other alloys, for example, aluminum 7000 alloys can have excellent mechanical properties, but you cannot use them when you are usually producing and casting. So how do we then make use of those alloys? We can use additive manufacturing. Okay, so therefore, the alloys which show an excellent performance, okay, in the laboratory scale, the new alloys what we develop, if they are not machinable, they are not castable, outwardly we cannot use them for engineering applications. And because of the additive manufacturing, we can also use those alloys which show excellent performance. For example, one of the implants what I show you, we are developing a new alloy based on the cobalt chrome the composition. And cobalt is toxic, okay, but cobalt chrome implants what we produce it for a dental and maxillofacial implant, okay, they show excellent properties. Okay, if the cobalt concentration is reduced less than 30%, in the conventional cobalt chrome they are about 60%. And if you reduce the cobalt concentration, it is good because cobalt is also toxic when we make implant. Okay, and the cobalt ions are released when the implant is in the body fluid condition, and this cobalt what is actually generating cobalt ions are very toxic for the body. But why do you need to have a high cobalt? Because cobalt helps us in improving machinability. So to produce an implant, we need to have some amount of cobalt so that the machinability can be achieved, so implant can be made. By reducing cobalt concentration less than 30%, machinability hampered significantly. But that alloy is excellent. Okay, strong, tough, good corrosion resistance. Okay, and safe for the human. And how do we use those alloys? Okay, so what we do is 3D print, additively manufacture those alloys so that those alloys, okay, can also be used with enhanced performance. And then we can also introduce deliberately the changes in the microstructure or properties as we build. Okay, layer by layer when we build, you can also change the parameters in such a way that so we can also introduce a complication and directional dependent changes in the component. Okay, so these are the important advantages, including the on-demand customization and manufacturing for implants, healthcare, and make part anywhere. And then you can also reduce inventory storage costs without any lead time. Good. After looking at advantages, then we know that additive manufacturing can be used effectively for various applications. And if you look at the broad type of additive manufacturing processes, there are about 7 types of processes. Okay. All the additive manufacturing processes that are available so far can be accommodated in these 7 types. Okay. And what are these processes? Okay. The first process, okay, which is actually commercially used, is known as a wet photopolymerization. The second is the powder bed fusion. Third is material extrusion, and fourth is material jetting. Fifth is binder jetting, and sixth is direct energy deposition. The seventh is sheet lamination. Okay, so all the additive manufacturing processes, what you see, can be accommodated in these 7 processes. We'll go one by one, quickly look at in the videos, and then we'll move on to the process chain. So what is the first process? The stereolithography apparatus. So this is the first process commercially developed by this Charles Hull. And in this case, so we take a photopolymer. Okay, what is a photopolymer? This photopolymer cures when it receives light photon. So we take the photopolymer, okay, in a container, which vat is a container, right? And then we selectively expose only at the locations where we want to create a solid by photopolymerization reaction. And these photopolymers can be acrylics, epoxies, or vinyl ethers. Okay, you see advertisement for paint, right? Epoxy paints or acrylic paints and so on and so forth. And we use those feedstock, and then we use a light source, either can be laser or ultraviolet. And what you see over here is a build platform, and then the photopolymer liquid is filled, and in the liquid state it's a monomer. So when the light falls onto this, then the monomer, okay, becomes polymer by cross-linking, right? So now the laser actually scan, and we have and selectively curing the photopolymer at the locations when the light actually falls on the earth. So once one layer is done, and we get the second layer by spreading the new liquid polymer, photopolymer on top of it, and then subsequently this process is repeated. Okay, and then finally we get the object made. Right, so this technique is known as a wet photopolymerization because photopolymer is kept in a vat, and then this photopolymer is cured by selectively exposing to light photons. So that's why we call it stereolithography apparatus, by the commercial term, but actual academic term is vat photopolymerization. Okay, the second technique is a powder bed fusion, and you must be hearing this technique as a metal 3D printer, okay, or various names, okay, like SLM, DMLS, these are all commercial trademark names, okay, but the actual name is a powder bed fusion. In this case, a feedstock powder is kept in the substrate, and then the laser or electron beam and selectively melts the powder. Okay, only when the laser is actually exposed and laser melts the powder to create a molten pool, and the molten pool solidifies based on the layer geometry what we are creating. So we first take the powder and spread it onto a substrate, and once the powder is spread, laser actually falls onto the spread powder, and then subsequently the laser melts the powder layer by layer. Okay, so we create a weld made at very fine and localized condition. Okay, so about 40 microns layer is welded with the previous layer, about 40 to 80 micron. And this process is continued, and subsequently once we finish all the layers printed, and then we take the final object out, and then we can use it for various applications. So what is the advantage of this process? And you get excellent surface finish as compared to the other metal additive manufacturing processes. And most of the cases, we use this for features, which are actually less than a micron. sorry, less than a millimeter. Okay, and the complex shape containing components, if you want to make it in metals and alloys, we use this process. Right, we can use a large amount of engineering alloys if, as long as the thumb rule is if the alloy is weldable, so we can also make use of this process. A disadvantage of this process is low productivity, because we'll have to spread the powder and the laser melts. So therefore, compared to other processes, and it is slightly slow. And when the laser power is low, and we use only sintering, not the melting, then we need to do post processing. Then becomes a multi-step process. Good. So third, the IT manufacturing technique is actually known as material extrusion. So in material extrusion process, so we actually use a filament. Okay, and the filament feedstock is extruded through a heated nozzle. Okay, and this nozzle at high temperature, okay, makes the filament fluidic. Okay, so when we take thermoplastics, for example, thermoplastic filament, okay, heated up and becomes highly malleable. So the heated thermoplastic is deposited through an extrusion nozzle, and the extruded malleable thermoplastic is deposited, and then it actually cures either naturally, or you can also do an activated curing. And this process, because we are extruding the feedstock, and the process is known as material extrusion. So this process is very famous because it is cheap, and we can also build your own setup. And most of the 3D printing equipment you buy in online, they are all material extrusion based. And we can also use a multiple feedstocks. If you have multiple extrusion heads, the one you can use it for support, and another one is use it for the feedstock material, but you use it to create a component, right? And the surface finish of this component is determined by the layer thickness and the bead geometry, bead dimensions what we create, and that can be controlled. And we can also use the different feedstock, so that we can also produce, for example, color components. Okay, by using the dyes, colors mixed with the feedstock, and then we can remove the substrate, because substrate either can be water dissolvable, or you can also just remove it to get the final component. Okay, and commercially this process is known as various names. For example, FDM, fused deposition modeling, which is actually nothing but material extrusion. FDM is a trademark of a company. Okay, so the fourth process is material jetting. So material jetting, as compared to material extrusion, here we use in material jetting a liquid feedstock, and this process is synonymous to an inkjet printer. Okay, what we have for printing. Yeah, so documents. So there, you take a ink, and then the ink is dispersed, okay, using a jet nozzle on a paper at the selected locations where we want to create the color. Okay, the black, or you can also use an RGB. Okay, cartridges. Similarly, here as well, we take a liquid feedstock, and this liquid feedstock is selectively disposed, okay, on a substrate. And the liquid feedstock can cure either naturally, okay, at room temperature and ambient conditions, or we can also photopolymer. We can let an ultraviolet ray, okay, and or some small heating element moves on top of the deposited liquid onto the substrate, and then the liquid cures, and you get the final object. The best the use for this equipment, this technique is to use wax molds to create wax molds for investment casting, or we can also produce multicolor components, because the feedstock is a liquid. We can also add some coloring agent, so to create a multiple color containing objects. Right, so material jetting, we use it, even in our research purpose also, to generate a multicolor components. Okay, multiple composition and gradation, and we can also change the polymer chemistry or even material chemistry. And people also use it, material jetting, for metals as well. For example, printed circuit boards, PCBs. Okay,
Excuse me, sir.
People use material jetting to print the entire PCB at one go, including the electronic components. and the connections, the backbone using this technique. The fifth technique, which is available,
excuse me, sir,
is binder jetting. So in binder jetting, what we have, it is similar to powder bed. Okay, but here the powder is not molten or sintered by heat source. So we selectively eject the binding agent onto a location where we want to create a consolidation. So binders are added only at the location where we want to create a consolidation. Right, so now the binder is added, and then subsequently we can let a small heater heat up the locations where binder is added, and the binder reacts with the powder, and then powder gets consolidated to create a solid object. Okay, so here we are not melting the powder, but binder is added, and then a binder is creating an agglomeration at the locations where binder is present. And then subsequently next layer of powder is added, and then what we create, the part which is actually green part, what we call it, and then subsequently we can take the green part out, place it in a oven, and further sinter it to get a final component. So we can also create ceramic components here, hard materials, because we are not melting anything here. So the tungsten carbide cobalt ceramic tool, we can effectively produce over here by creating a feedstock mixture of tungsten carbide and cobalt, and then add binders, and then subsequently do a post-process sintering, to get a nice ceramic tool. And the sixth process what we have when IT manufacturing is a sheet lamination. Sheet lamination, it is truly, it is not like another process, because here we use both layer by layer manufacturing and machining in combination of both. So here feedstock is a thin foil, and this thin foil is welded with the substrate and then previously produced layers by solid state welding, for example ultrasonic consolidation. So also ultrasonic consolidation, the joins the foils with the previous layer, and then a machining head would remove the unwanted regions in a layer. So here foil is going, feedstock is welded, and then the regions which are not required, which are not part of the design, are removed out by either machining or by milling, whatever way we want to create that. Right. So, and this is a neat technique to produce components, right, which can also be smart. For example, the actual joining process is taking place at ambient temperatures when you use ultrasonic welding. Right, so we can also introduce some sensors inside between the layers. Say for example RFID tag or a load sensor, or subsequently when we want to analyze the performance of the component, like in the braking situation, for example brake shoe, we can produce by sensors inside which can also predict the braking sequences, for example. So people use this technique, sheet lamination, to produce smart components by using and layer by layer production. Yeah, sixth technique what we have is actually known as a direct energy deposition. So DED is similar to what we have for welding, or cladding, laser cladding. And in this process, a feedstock is fed. Feedstock can be either powder or wire. In this case, what you see in the video in my pointer, a laser source and a powder. Powder is fed onto the laser, and the molten powder, because of the laser interaction, the powder melts, and then powder is deposited, on top of a previously solidified layer, and then we keep adding the layers to produce a final part. And this is actually known as a direct energy deposition, because the feedstock is directed to the energy source, and then the feedstock melts fully, and then molten droplet is transferred. So the feedstock can either be powder or wire. The heat source, primarily we use laser, electron beam, or arc plasma. Like here it is a laser and powder, and this technique So here we use a laser and wire. Okay, so laser and we use a wire is fed coaxially onto the same axis of the laser axis, right? And then wire melts, and then subsequently the molten droplet, okay, is created, and then it is deposited. So it is a laser with wire feeding, laser welding. So layer by layer we create, and we can also do electron beam with wire, okay, where the electron beam heat source is used to melt. Right. So for example, we can feed the wire onto the electron beam path. The wire can be molten and then deposited. The advantage of using electron beam is we do entire activity in a vacuum chamber, so very sensitive material can also be printed using this process, and is highly energy efficient compared to laser. We can also use a simple welding setup. Okay, so this welding setup, what we have is a gas metal arc welding torch, and then we deposit layer by layer the welding setup using a welding setup, and then subsequently we can also use a machining tool to finish the already deposited layer. And this technique, people also call it the wire arc additive manufacturing, but the actual term is a DED process using arc plasma. So it's arc wire DED process. Okay, so what you see here is one of the setups what we have, which also can combine both deposition and then the machining together. Right, so if you look at the entire additive manufacturing spectrum, so all the processes can be classified into these 7 categories. Right, so there are the other processes, for example, friction deposition. The friction deposition, that is also one of the DED techniques what we classify, or cold spray. All of them can be classified under DED process. Good. So if you look at the generic process chain, out of all the 7 processes, okay, so the process chain what we use, we start with the CAD design, and the CAD design is 3-dimensional data set, isn't it? It has an X and Y Z information. So first we convert the CAD drawing into a more and a suitable format for additive manufacturing. So we convert a CAD drawing into STL format. The STL format is nothing but to describing the contour of the object, okay, by sets of triangles. Right, so any shape can be defined by filling it with the triangles, right? And these triangles, okay, would define the outer contour, and then subsequently we slice this STL file based on the layer orientation. Suppose if you want to print this object along this direction, so we slice it based on the layer thickness, and each slice, okay, is then created individually by layer. So we slice it, and then each slice we can create and path planning using path planning strategy. So these layers can be created by either using a DED process. You need a robotic arm, and then a control power source to deposit, and then subsequently once the deposit is made, we can machine to create a final component. Okay, so first step, as I said, it is to convert the CAD into an STL file format, isn't it? It's the first step. Why we need this? Because you don't need 3-dimensional data format. So in STL file we convert from a CAD data. Okay, so if you look at the STL file, what we have is the contour of the object can be described by these triangles, and these triangles can be then best described by their vertices and the surface normal. So once you identify the coordinates of these triangles, okay, so then we can construct the object using this file. And STL file is important because this enables us to slice. So imagine if you want to build this object, vertical up like this, and one layer is here. When we slice on that layer, and we can identify the interaction points of the cutting plane with respect to the vertex positions by connecting the cutting points with respect to triangles. We define the outer boundary. Okay, the boundaries of the objects. Okay, so once we have converted into an STL file, the second step we use it for slicing. So in the slicing, so what you do? So we have triangularized STL format, and then we have a slice, and slicing can be done in various ways. For example, to get a complex nonlinear geometry made, so we can also change the slice thickness, layer thickness based on the geometry. Suppose if you use a uniform slicing layer thickness to produce such a non-linear object. Okay, so we end up producing just by like like a staircase. Okay, so the surface roughness will be very poor. So instead of using an uniform layer thickness, we can also use layer thicknesses changing as a function of build orientation, build direction. And this is actually very beneficial to get a good dimensional accuracy and improve the surface finish. And this is what we call it as an adaptive slicing. Okay, some cases we can also do a multi-directional slicing. For example, produce such an overhanging features. In a powder bed, we may have to do with the support structure. Support structure, what you see here in the orange color. And if we want to know produce this part without support structure, say for example, powder bed, it is not possible. But when you use a DED process, we can also manipulate the direction. What I showed you in the video in laser and powder, the build platform can also be rotated. So for that, we need multiple directional slicing. Okay, multi-dimensional slicing. Okay, so we can start printing only the B1 part of it, and then subsequently the build part can be rotated 90 degree and then build the B2 part, and then 45 degree for B3 parts to produce support-free objects. And this is what is known as a multi-directional slicing. Okay, to produce such an overhanging features. Okay, in a DED process or the process where it can be manipulated, the substrate, we can use the multi-directional slicing as well. So once slicing is done, the next part is to achieve this sliced layer. So that we do it as a path planning strategy. So so various path planning strategies we can use. The most common path plannings are raster or which is known as a unidirectional scan. So it will move along one direction, or zigzag, the bidirectional scanning. But there are disadvantages of this process of doing simple unidirectional and bidirectional scans, because of the fact that when you use a bidirectional scan, you expect a lot of residual stress generated, and the surface finish also very poor. So instead of doing that, so we also can do what is known as a contour path planning. Okay, in contour path planning, so the layer is created always by creating a beads parallel to the outer contour of the object. Like for example, here we see a layer we'll have to create. And in a contour plan, what you do is we start producing this layer by creating the beads parallel to the contour of the surface. And we also follow some strategy. For example, starting from outside to inside, when you produce, you always incur some voids at the middle part, right? And that is not really recommended. So instead, what you do is we identify first the medial axis, middle axis of this layer, and then start from inside and going outside. Okay, so then we end up producing a very nice layer, and this is what is known as a MAT, medial axial transformation, and then subsequently using contour planning. And there are a lot of advantages in terms of containing heat, so that cooling rate can be reduced, and then subsequently we can also get a good microstructure. So we identify required path planning strategies, and then we'll also ensure that the minimum start and stop of the heat source to produce void free and without crossing the path, and get an excellent part accuracy. Okay, so these are some of the examples. For example, this is for a fuselage and aircraft, and how the contour path planning can be used. So this is a CAD drawing. This is a single layer, and we identify the medial axis, and then subsequently we can start depositing by following the starting from medial axis and then finally producing the final component. Good. And these are some example components what we printed using DED process in collaborators place, and using a technique what I explained earlier, right? And we can also manipulate these slicing and path planning strategies to our advantage, because path planning strategy is one of the important to change the cooling rates, temperature gradients that are prevailing in the solidifying molten pool. By carefully manipulating these, we can also see the microstructures, therefore properties of the component as well. Okay, so having said all of them, we're almost approaching an hour. There are challenges, in additive manufacturing. The biggest challenge what we'll have to look at is the defect formation, because as I said, if you use the metals and alloys and DED or laser powder bed, it is a multi-pass weld. So whatever defects you may expect during welding, you may also see here like porosity, lack of fusion. So all these things you need to control. And the other challenge is anisotropy. The microstructure what we generate would always be directionally dependent. So the properties will vary as a function of directions. And we have shown that by carefully understanding the physics of the process and subsequently controlling the process parameters, we can avoid all these defect formation and anisotropy. And the second is the speed and productivity. So IT manufacturing as such cannot match the conventional manufacturing. Okay, in terms of productivity. If you look at the overall development, okay, for very specific components, for example, a forging die. A forging die, to make a forging die, it takes about 3 months, start from an initial casting process, machining, before that heat treatment to solutionize, anneal, and then do a machining, and then final polishing and heat treatment, and then use. And then that die would be used for hardly an hour. Otherwise, if you use more than that, the die would collapse, crack. So we spend about 3 months total time to make the die, and then it will work for 1 hour, and then you'll have to be completely scrapped. So such applications, the IT manufacturing comes in very handy. They can also introduce complex cooling, so the die life can be enhanced. Entire die can be printed directly from design within a day. So the productivity as such cannot match. If you want to produce a very simple component by additive manufacturing, it will not work out. Okay, so to enhance the product development and produce the components which are amenable for additive manufacturing, so its speed and productivity will be advantageous. And the design complexities, it's unimaginable. You can visualize yourself. And the accuracy and surface finish is always a problem because it is, as I said, it's a weld. Okay, so we'll have to look at what is surface finish we require, and we can also control the surface finish by the various strategies. And then finally, as I said, it's a fully automated process. The entire process is actually governed, okay, by various computer programs, algorithms, what we use, starting from converting the STL files, slicing and path planning, process control, everything. So therefore, considerable amount of programming knowledge is also required. Suppose if you want to take up IT manufacturing as a career. Good. So with this, I'll wind up because exactly in about an hour. Okay. So thank you for your kind attention. And if you have any questions, I'll take it up. Okay. Or else you can also visit my homepage or YouTube pages and so on and so forth. So you can find a lot of interesting stuff. Good. Thank you for your attention.
Thank you, sir, for your wonderful session. Participants, any doubts?
Yeah.
Is asked to unmute if self queries.
Yeah, looks like is it all clear or?
Dear
participants,
please
and ask to.
And that's okay. Even if the questions are not there, no, it's okay, fine. No, we can always email. It's not be an issue. Yeah.
Thank you, sir.
Thank you, sir.
Yeah.
Full session.
On behalf of management, Ballari Institute and Management, Ballari, I thank Chairman and Director Dr. Yashwant Bhopal sir, Deputy Director Professor Vijay Prithviraj Bhopal sir, and Principal Dr. Edward Basara sir. Thank you for your support for successful conduction of first week online ATAL FDP. I thank ATAL Academy, Government of India for sponsoring this FDP program. On behalf of organizing committee, Department of Mechanical Engineering, BITM Ballari, we extend our sincere thanks to your good self and for your valuable time and expertise given to this ATAL Faculty Development Program in advances in additive manufacturing. Thank you for your inputs and enthusiasm on the topics you have presented, which are most helpful and valuable to the program. Thank you, sir. Thanks a lot. And thank you, one and all.
Thank you. Thanks. Bye-bye.
Hello. Hello.